Nice.
Okay, so we're all here, so I'm going to give a brief introduction. Who is new, who's never been here before? Sweet. Excellent. So this is the Portland Linux Unix group. That's why we allow apples in the room, because they're running Unix underneath also. Our previous, the person who used to do this coordination before me is like a strongly BSD person. So all of the, in fact, that's why I'm here now, is that I used to complain about all the sort of the BSD heavy speaker contingent, and so I felt it was incumbent on somebody to come up with more speakers with maybe a little broader. Nothing wrong with BSD, but you know, a little diversity. That's who we are. We're going to have a clinic. We have a monthly clinic where we help people fix problems. We've been having that since, I think, last May. This coming month, as opposed to where we've been recently, we're going to be at the Albina Branch Library on the 15th of February, which is the second Sunday from now. And we hang out for about 4 hours, and people potentially come and we help them do stuff. We've had a guy, one of our previous speakers, a guy who talked about post-market OS. There, if you got supported Android phones or tablets or Chromebooks, he can help you put post-market OS on them, assuming there's support. The first time he came, I brought a box of my old devices, and you brought something, and he struck out on all three things. But in the interim, we've come up with other devices, and he's actually successfully done the thing. And unfortunately, I've been paying attention to other people, and so I have no idea how he did it. So that's the clinic. We have speakers, actually this month, next month. And in fact, we have the speaker for next month in the room. And then April, we have a different speaker. And then after that, I don't have any more friends. So, you know, again, I'm just reiterating that we need to generate speakers. If you have any ideas, if you want to talk yourself, or if you know anybody you think would be super awesome to talk, have them get a hold of me, and we'll line you up. After the meeting, a bunch of us go to Patty's down at First and Yamhill and hang out and have a beer or a beverage of your choice, and various food items as it suits you. So we have a speaker this evening, and I'll let him introduce himself.
Thank you very much. My name is Jacob Hoffman-Andrews. I'm a senior staff technologist at EFF, and I also work for Let's Encrypt through my work there. I wanted to just double down on Russell's recommendation to speak. I asked him, what should I speak about? And he said, just speak about what gets you excited, what you like to speak about. And that's what I'm going to do, and I'm excited about it. And I bet every single one of you here has something you're excited about and you could speak about. So like, help your fellow Linux and Unix group members out and come give an interesting talk. Hopefully this one will be interesting. So you all raised your hands pretty much. I think you know what these organizations do. I also have one more slide about certbot. So EFF makes certbot. It's not in the name, so I just want to make sure everybody knows. Often we'll go to a conference and table, and people will be, you make certbot? I love certbot. That's great. So EFF makes certbot. Spread the word. So what I want to talk to you today about is the certificate transparency ecosystem in 2026 and some new things that are happening with it. And what is certificate transparency, and why are these new things happening, and why should you care? To start at the beginning, Let's Encrypt is a certificate authority, and we produce certificates for people to use to encrypt their website so they can do HTTPS. The status quo is, and has been for a long time, that every publicly trusted CA can issue a certificate for every website. And this is kind of dangerous. It means that you might have your CA you go to, but some attacker can go to another CA, or even your CA, and try to get a cert. And if they are compromised or malicious in some way, they can get that cert, and it will be fully trusted by browsers. And this has happened, and it's been used to intercept traffic. And for a long time, the status quo was actually CAs did not publish the certs they issued. And they would even say, oh, this is a trade secret. It's private information of our customers. We can't publish that. And there's some value to that in that, say you own a public website, but you're launching some new product and it has a new subdomain that would be like a spoiler for what your new product is. You might actually not want the certificate for that to be public before you go launch. But the flip side is if CAs don't publish all their certs, then we don't actually have a detection mechanism for when a bad cert gets issued. And so we can't go get it fixed. We can't tell that CA, hey, you're compromised, go fix it. Or, hey, you actually look kind of malicious now, you're going to get distrusted. So certificate transparency, the RFC came out around 2013. Let's Encrypt has logged to it since the beginning. One simple question is like, well, OK, say there's a mandate. CAs must just publish all their certs. Why don't they just put it on their website? Why do you need a protocol or anything fancy like that? The way you would use a malicious certificate to attack somebody is if you already have control over their internet connection. So maybe you are their ISP, or maybe you are a national government. You can intercept their traffic somehow, but you can't get at the GUI insides because it's encrypted, and you don't like that. So in order to make use of a malicious certificate, you need some sort of network control. And of course, if you have that, you can also hide the fact that the certificate was issued from the browser. So we need a couple things from a certificate transparency. It needs to be verifiable by the browser. And we also want it to be tamper-proof. We don't want, for instance, a CA and a log to be able to collude to say, oh, we're just, this was entered in the log, so this user believes it's valid. But actually, we're not going to tell the rest of the world about it. We're just going to, in this zone of the internet we control, we're going to lie about it. Where did I have this? Yeah, Merkle trees. How many people know what a Merkle tree is? All right, cool. So the short version of what a Merkle tree is it's an append-only data structure, or it's a verifiably tamper-proof data structure. So you can imagine a sequence of items that you want to keep appending to. And one way to do this would just be to hash it. It's like, OK, the hash at time t was this, and the hash at time t plus 1 is this. And if you want to know that all of these bytes are the same as those bytes plus a little more, you can download all the data and compare it and check the two hashes. But it's very inefficient. It's very slow. So in a Merkle tree, the leaf nodes, the bottommost ones, contain your documents. That's a certificate. So D1, D2, D3, those are certificates. The node right above those contains the hash of that certificate. The node above that contains the hash of the two nodes below it. So as you build up this tree, as you log certificates over time, you build up that lower level, and then you fill in the tree above it with the necessary hashes. And the nice property this gets you is if you're way off here on the right and you just saw a new thing added to the tree, and you want to know, is the overall hash of the tree now that someone is attesting to consistent with everything else we saw in the tree before? You don't actually have to have all that data. You don't have to crunch all that data. All you need to know is what the hash was before, or what essentially a leading edge worth of hashes is. So what that comes down to is it's about logarithmic time to validate these properties of the tree that you care about. So I'll remove this distracting animation finally. So as a CA, what we do is we sign a special certificate called a pre-certificate. And it actually has a poison extension in it. So that's not one you would actually put on your website. And in fact, if you did, a browser would reject it. Because the poison extension says, I am critical, which means if you don't understand this extension, fail. And of course, the way to understand the poison extension is also to fail. The reason we do that is it's certificate shaped. and then we submit that to a CT log, and I'll get in a second to who those entities are, and they stick it in the list and send back to us what's called a signed certificate timestamp, which says, as of this time, I received your certificate. I promise, up and down, I'm going to add it to my log and keep it there permanently. It hasn't happened yet, but it'll happen soon. And we have to do that to a couple different logs, because if there's just one, they might be colluding with us. And also, CAs are allowed to run their own logs. So for instance, Let's Encrypt does run some fairly big CT logs, and they're on our list, and a lot of our certificates get logged there and one other place. We need a minimum 2 places. Once we get back our SCTs, we go into that pre-certificate we made, we tear off the signature, we rip out the poison extension, we squeeze in the SCTs we just got back from those 2 logs, and then we sign the whole thing again. That's the final certificate. That's what gets delivered to CertBot or your other Acme client and installed on a web server and downloaded by a browser. So the CT enforcing browsers, of which there are now all the major browsers enforce CT, they have a list of CAs. They also have a list of CT logs and the public keys for those CT logs. So once they've validated that the cert is signed by a trusted CA, they will also verify that there's at least 2 logs that the browser knows about that promised they would eventually incorporate this. So the reason I bring this all up is, well, this is a little foreshadowing. I'm not actually going to get to why this is important until later in the talk when I talk about post-quantum cryptography. But note that there's 3 signatures. There's the Let's Encrypt signature, or the CA signature. There's 2 signatures from the logs, which are generally ECDSA today, but won't always be. And then there's the public key, which is the subscriber's public key. So the subscriber is the website owner, whoever's running the Acme client. So you generate a key pair, and the public key goes in the certificate. So the first of the cool, exciting things I wanted to talk to you about today is called the static CT API. So the design of certificate transparency from the beginning was around this idea that you would have a lot of people kind of submitting certs all at once. You don't want them to block on each other. You don't want everything to slow down while you do the sequencing, putting everything in that tree, recalculating hashes. It doesn't take that long, but there might be stalls or whatever. So that's why we have this pinky promise, the signed certificate timestamp. It's like, OK, you might be accepting from a lot of different points at once. You might have multiple front ends. They won't have the official view of the tree for a little while. Then there's this sequencing step that happens. Additionally, the way that monitors and the public gets data from certificate transparency logs is fairly simple. You say get entries, it's an HTTP endpoint, and you specify a start and an end. And these logs have well upwards of tens of millions, hundreds of millions, easily hundreds of millions, I think actually in the billions now of certificates. So obviously you can't specify start equals 1, end equals a billion. Nobody wants that. So most logs will apply some sort of limit and say, oh, you can get 256 of them at once. This is a very cache inefficient way to offer this view. People can kind of get these chunks from anywhere in your log, and it's just rather expensive. The other aspect of how traditional CT was run operationally is most people outside of Google. I promised to tell kind of who the operators are. So like Google developed CT. They were one of the first log operators, but for them to just be like, yeah, we're just going to run the logs and everybody just trust us doesn't work very well for the internet. We don't like that. So they had to kind of drum up support from other organizations. Cloudflare also runs a log. Pretty much everybody else who runs a log is a CA, and a lot of them are the big CAs, so Sectigo, DigiCert, and Let's Encrypt. So that's one fragility in the ecosystem. There's actually just not that many log operators. And one of the things that sometimes happens, there's these verifiable properties of Merkle trees. And if a log violates those properties through operational error or a bit flip, or just like they're down for a while, and so they promised to incorporate some certs and didn't do it in time, that can be indistinguishable from malfeasance. And so the ecosystem needs to be able to distrust those log operators. So ideally, we would have a lot more, but the logs are very expensive to run. And sometimes they go down. And there's just really not a lot of incentive. You're not allowed to charge for running a log. The browsers don't like it. They really want every CA to be able to submit to logs. They want every member of the public to be able to download from logs. And I forgot to kind of get around to, actually, these have been hugely beneficial to the ecosystem. In the years since CT has been deployed, an enormous amount of CA mistakes have been discovered just by looking at CT logs. And several of those have resulted in investigations or kind of like patterns of looking at series of mistakes that have led to CA distrust. Like it's made the whole ecosystem more transparent, more trustworthy, and even the little mistakes that don't add up to distrust, all the CAs get to learn from this in public, and it's made everybody better. OK, so yeah, getting back to here. So traditional CT logs, most of them were doing some sort of relational database type thing, like MySQL or MariaDB. And there's a couple reasons why that's not great. For one thing, they tend to want to run on just like one big server, and the bigger your log gets, the bigger your server. And first, we sharded the log. So it would be like, this log contains just a year's worth of stuff, and then next year we're going to spin up a whole new log with a whole new key. And then we did, well, actually, we're going to do a half a year at a time. And even then, we were seeing like 7, 10 terabytes of data in our logs, which gets like really expensive to run a database instance that can handle all that. Databases really love to like keep as much in memory as they can. This is way more than we're going to fit in memory on a typical instance. And then you have random users from across the web kind of random accessing your data and causing a lot of churn. So the static CT API, one of the core concepts here is, well, rather than let people get up to 256 items from any point in the thing, let's just let them request essentially a file. And this file is file 0, and that's the first 256 items. And the second file is file 1, and that's the next 256 items. And so it's always the same. There's only discrete items you can request. And actually, one of the really cool properties is that these are append-only logs. Once that first tile is full, once more than 256 certificates have been put in it, it's never going to change. You can use immutable caching. You can just cache it forever. You can make it really cheap to serve. It also, this style lends itself well to object storage. Let's see, did I mention object storage here on this slide?
You did it right there.
Cool, great. Yeah, there we go. Object storage rather than relational database. So object storage is essentially something like S3 or Backblaze. You could also think of it as file storage. So in particular, if you're running this on some sort of cloud, like most cloud services offer some form of object storage for really cheap. They love it. It's like extremely distributable. They're just like, yeah, that key's going to go over there. That key's going to go over there. You can serve it off of lots of cheap machines. You can replicate it. And the guarantees that this tends to offer are less than relational databases, but you can map the requirements of CT onto it pretty well. And yeah, one of the nice tweaks in this ecosystem transition that's happened is I talked about this pinky promise. I was crossing my fingers when I said the promise, but I think I meant this. A pinky promise to add to the log later. And this is actually like a really big foot gun, because if a CT log accepts a cert, oh yeah, OK, here's your signed certificate timestamp. I will definitely get that done for you very soon. And very soon is at least within the day. It's a very generous time, but the minimum merge delay is a day. And then your data center is struck by lightning, and you're instantly down for a week. You have blown your minimum merge delay. Your log can no longer be trusted. That's indistinguishable from malfeasance. Well, there's actually two signed things in the CT ecosystem. There's these little promises that you get along the way, and periodically, once an entry has been sequenced, it's been assigned its absolute number in the log that's never going to change, and all the hashes have been computed, and you get a tree head. Like, what do all those hashes come out to at the top of the tree? And then the log will sign that too. It's called a signed tree head. And one of the ideas that most static CT implementations do is when a CA submits to us, rather than get back to you within small numbers of milliseconds, yeah, it's an HTTP request. You can wait a little while. You can wait 5 seconds for an HTTP request. It's fine. So we'll kind of buffer everything that's been submitted during a particular period of time, and then we'll sequence it. And we'll put a cap on how long we're willing to buffer, like a second. And so we'll sign a batch, and then by the time we return that SCT, we know exactly where in the log that cert is going to go. And in fact, there's an extensions field. So the SCTs you get back from the static CT API can include this extension that says, and here is the index where you'll find it in the log that offered it. And so this actually removes a massive footgun, because if your data center gets struck by lightning, all you lose is the buffer of stuff that CAs were waiting for anyhow. They just had an open HTTP connection. It dropped. It's just an error. It's not a big deal. They will go talk to some other CT log. So already you're starting to see there's some pressure on logs that are getting bigger and bigger and bigger. There's more and more certificate issuance. They're expensive. Operators have been dropping out. Static CT API helps a lot. So they should clarify, quantum computers throw a wrench in CT in general, not specifically to static CT API. So that's relieving some pressure, but there's even more pressure on the ecosystem coming up. So just to review real quick, a cryptographically relevant quantum computer, which is significantly bigger than anything we have today, which are in the small numbers of qubits, but a larger quantum computer, which we have reason to believe might arrive eventually and in the not too far future, can crack public key encryption very quickly. It can factor numbers, in a much faster amount of time than a classical computer. And so that'll kind of break all the encryption on the internet. And we can't really afford to wait until the day that a cryptographically relevant quantum computer arrives, because by then it takes a long time to develop and test and analyze cryptographic algorithms, and then it takes even longer to actually deploy them. So now is the time to act. It's been the time to act for a while, but now action is starting to happen. I like to mention specifically post-quantum cryptography is cryptography that works on the computers we have now. It kind of plugs in the same way, it works the same way on the internet, and is resistant to a quantum computer. Quantum cryptography, which sounds very similar, is something totally different, and it's about entangling atoms so that you can communicate and know if somebody's tampered. It does not just work on the internet as we know it. So it's not that interesting. We're interested in specifically post-quantum cryptography. So the monkey wrench here is that the algorithms that have been invented for post-quantum cryptography are really big. So ECDSA, which is very well distributed today, lots of people use it, is really nice and small. We've gotten used to nice small key sizes, nice small signature sizes. And let me actually go into what MLChem and MLDSA are. So ML stands for module lattices. So this is this spooky math that the cryptographers have been busy coming up with that's actually difficult to crack for quantum computers. There have been a lot of different kinds of spooky math, but these are the ones that kind of survived the competition and didn't get cracked along the way. And NIST is these are, we think, probably good enough. Go ahead, start deploying these. And MLChem is nice and fairly straightforward. Chem stands for key encapsulation mechanism. And you can think of it kind of like Diffie-Hellman. So when your browser connects to a website, there's a handshake. And part of the handshake is the certificate. That's how you know you're shaking the right hand. And so that's a signature. And then there's also a piece of data that both sides offer to say, hey, here's something I have, and here's something I have, and let's mush these together, and we're going to come up with a symmetric key, so an AES key. And then we're going to encrypt the connection with that. And there's been different ways to do that over the years. Diffie-Hellman is kind of what we do today. Or elliptic curve Diffie-Hellman, and it has some nice properties, and it's familiar. Chem, key encapsulation mechanism, works differently, but it's the same kind of concept. You take some values and you smush them together, and you get a symmetric key to do the rest of your session with. And that's actually out. Chrome has some kind of experimental implementation on the client side. Cloudflare has some kind of experimental implementation on the server side. So like your browser may actually be doing this live with some websites. Now, MLChem is like probably good enough, but there's, it's still very new on the scale of cryptography, and new cryptanalysis might come out that breaks it. So right now the deployments are very conservative, and they kind of do 2 layers. They do a key derivation with X25519 plus MLChem. MLDSA isn't really rolled out in practice yet. You can do it in a private PKI, like if you're installing your own root certs. Might be a fun like home lab experiment. But you can't use a publicly trusted MLDSA cert on the public internet yet. And this is part of why it's not deployed. There's just monster key sizes and signatures. And it may not seem like that much in a world where web pages are like a megabyte plus. But this has actually been like measured to cause noticeable slowdowns. And part of that is, this is actually at the very beginning, or almost very beginning, of trying to connect to a website. Like the very beginning is your DNS request. But then like right after that, you do your handshake. And a website, of course, is composed of many resources. And none of those resources can even start their DNS lookup and their TLS handshake until you've finished with that GET. And so a slowdown right here at the beginning slows everything down. Also, if it gets big enough, this can overflow your initial congestion window. And so you have like an additional round trip time. So this sucks and is like probably not going to get deployed as is. And remember what I said about right now there's at least 3 signatures per certificate. So that 2,420 bytes, multiply it by 3. Oh, and then, yeah. And then also there's that public key in there, right? So every cert has that public key. And all of this has to change.
How many packets would that be?
It depends. But yeah, it gets messy. The other thing I want to say is part of the reason MLChem is like being deployed now and MLDSA is a little more relaxed is if that key agreement mechanism is cracked, what that means, and when I say cracked, by a quantum computer, if somebody records the traffic, they can retroactively look at the handshake and crack that key agreement. So for instance, the key agreements that happen today using elliptic curve Diffie-Hellman, somebody collecting those could apply a cryptographically relevant quantum computer in the future and decrypt them. And then you have the session key and you can decrypt the data. So it's a store now, decrypt later attack. So the earlier we get that stuff in, the more we protect the traffic of the future. The traffic of the past, well, that's going to be compromised. And that's just the way life is. For signatures, being able to crack a public key that's used for signatures really only helps you if you're live intercepting the handshake and imitating someone. All right, so what are we going to do about it? Oh yeah, I had a little diagram here. So this is an extremely simplified certificate. I tried to paste in the OpenSSL dump of a certificate in here, and the text became ridiculously squinty. So I deleted way more fields than I thought I would have to. But you have your issuer, your subject. This is the public key of the website, essentially. These are your 2 SCTs. And you can see they're using ECDSA with SHA-256. And then down here is the overall signature from the CA. So something called Merkle Tree certificates is the new exciting thing. There is a new working group at the IETF just chartered called the Plants, which is PKI and some other stuff. They made up an acronym that's pretty good. It's full of a lot of plant puns, too. Now, I mentioned certificate transparency fundamentally uses Merkle trees, but these are Merkle tree certificates. So it's like, what if we took that Merkle tree concept, which is already fundamental to the process of issuing a certificate, and we actually made it more fundamental. So the shape of the certificate, the bytes it's made up of, will change. If we adopt Merkle tree certificates, this is the proposal, is that certificates will change to use proofs from a Merkle tree as part of their structure. I'm going to take a short break and have a sip of water. So right now, CAs kind of voluntarily run their logs, in part because it's an availability risk, right? Like at Let's Encrypt, we know that if we can't find enough logs to send our certs to, we will just be down. We won't be able to issue certs that work because we won't be able to get enough SCTs. But in this, and there's also, we are kind of required to accept any commerce. So we have to take other CA certs, which we don't mind because we're like one of the biggest issuing CAs. That seems only fair. Everybody else is taking our certs. That's fine. But if you are a small CA that doesn't do a lot of issuance, it doesn't look as worthwhile for you to stand up a log where you're going to receive certs from everybody, including the big CAs, and serve to everybody, and you only issue a small number yourself. In this world, the idea is each CA will run their own log, but they will only be responsible for their own certs. So nobody else gets to submit to it. But everybody does get to read it. And also there are third parties who kind of copy it. So when a CA wants to issue a certificate, rather than submitting it to some external log, first they submit it to their own log. They sequence the log, they sign a checkpoint, which is like the signed tree head concept. And then they've got kind of, that's the signature that will act as their CA signature. So it's kind of, instead of signing the cert, they write the cert to a log, sign the log state. And like you could kind of ship it like that, except that's actually worse than today because you don't have any third-party observation in there. So we want to get at least the nice properties we have today where there's some other party that's saying, hey, I saw that cert. So there's this notion of cosigners. So cosigners consume that CA's log, and they consume the signature on those checkpoints and say, oh, yeah, OK, I verified the properties of this log. It's append only. I saw these certs. Maybe I have a copy. And here's my signature that attests to that fact. So the CA, after sequencing the cert, signing the log, they go talk to this cosigner and say, hey, can you give me that signature that attests that like my log is doing good as of this point? And they're like, here you go. So now the CA has two signatures, kind of smushes those together, and then you've got something that is roughly, certificate body plus CA signature and a third-party signature. That's their certificate. So we've cut out like one signature already. That's pretty good. There are some other optimizations in here. So the logs that the CA runs would be changed from today's CT logs by the thing that you put in the log is shaped. It's the same shape as the certificate, but where the public key of the website goes, you rip that out and you put a hash there instead. And the idea is when a browser gets that cert and is trying to validate it, the actual cert that the browser gets will have the public key there. That's needed to validate. But the browser can validate that against some tree or can gossip the necessary information to validate it because it knows the public key, and then the hash is verifiably connected to it. So that allows the logs to be significantly smaller, particularly in a world of post-quantum certificates where the public keys would be very big. And then there's this really fancy concept that I didn't go into a lot of detail because, honestly, I still need to understand it a bit better. But there's these signature list certificates. So you can take the Merkle Tree certificate concept even further and say, OK, well, the browsers actually ship a lot of state to their clients already, stuff like safe browsing lists. And even within the PKI ecosystem, they ship revocation lists. So I'm like, as you know, but you probably so revocation is a big problem in PKI. CAs maintain a list of all the certificates that have been revoked. It's way too big for any individual browser to want to download all the time. And so browsers fetch them all proactively, make a Bloom filter of those, send them down. And so the end user's browser can check that Bloom filter and be like, oh, this might be revoked. I'm going to go actually fetch the list and get a signature from the CA. Yeah.
What's a Bloom filter?
Oh, thank you. So a Bloom filter is a data structure that kind of can tell you, is this in the set or not? Very sparsely, very compactly, but with some false positives. So you take a big pile of, say, URLs, and you do some math to it, and you get a small number of bits that somebody can take their URL and check and say, OK, this is definitely not in the set, or probabilistically in the set with a probability that you can adjust based on how big you want the object to be. Thank you for the great question.
The classic way is if you wanted to build a spell checker, you had a list of words. You take the hash of all the words, set a bit in some size array, and then you could just say, oh, is this word set in that array at that bit? And then you could say, that's probably a spelling error, but I can't be sure.
Gotcha.
So anyhow, what if browsers shipped some additional state? So now you've got your dozens of CAs out there. They've all got their individual CA logs. The browsers are probably following those logs with interest because it is relevant to the security of their users, and can kind of download latest state from them in the form of landmarks, kind of similar to checkpoints. It's like, here's the latest state of that log, and can update the actual browsers running on people's computer to be aware of the status of those logs. And so then, instead of sending so when the browser handshakes with a website, the browser can tell that website, hey, I know everything there is to know about all the CA logs as of yesterday, 10 p.m. And the website can say, great, well, my certificate was issued way before then. It's included in a landmark by then. And so instead of sending you these big, heavy signatures, I'm going to send you an inclusion proof, which is a series of hashes that's like, here's how you find your way from that landmark to my cert in the tree to prove that my cert is in the tree. And those are, because those are hashes, they're actually way smaller than these MLDSA keys. So the bytes on the wire from the browser go back down to a reasonable number. The bytes in the log the bytes in the log are also really good because remember, what the CA put in its log doesn't have any signatures in it. It's just I talk about the guts of a certificate. It's technically called the TBS certificate or the to be signed certificate. It's everything in the certificate but the signature. So that's what goes in the log minus the user pub key plus a hash. So the logs also get to stay nice and small, and the signatures are all kept track of outside of it. Oh, one more thing that I thought you would all like. We launched IP address certificates. So yeah, you can get an IP address certificate. The currently out certbot does not support it, but the one going to be released in just a few days will support it. I added that implementation. It will support it with the standalone manual and I think probably also WebRoot plugins, but not with the Nginx and Apache auto configurators yet. And there are also some other Acme clients that you can use to get them. You should know you need to select a different profile. Profiles are also something new within the last year we added. So when you request a cert, you can request a certain profile. One of the reasons we added that is so that you can request a short-lived certificate. So right now, certs are 90 days. If you want a 6-day certificate, you can get that by saying, I want preferred profile, short-lived. If you want an IP address cert, we actually require that you get a short-lived one. And the reason for that is in today's world of cloud computing, often people don't actually control their IP addresses for very long, often even much shorter than 6 days, but that's a compromise. But you could imagine I spun up my EC2 instance and I got my IP address and I got my IP address cert, and then I tore it down 10 minutes later, and then somebody else brings up theirs and they get the same IP address. We don't really want those to coexist for very long.
You will support renewal though, right?
Yes, exactly. So renewal should be automated. So in theory, 6 days should be no problem because you have automatic renewal. We also have something called ARI, Acme Renewal Information, which tells your Acme client when to renew.
Can you have both for the same IP/name? Okay.
Yeah, so you can do two things. So what I would probably recommend is, it really depends on your use case. In general, I think IP certs are a fairly niche use case, and most people are better off just doing it for the host name. But if you have some box and you want it to serve an IP cert and you want it to serve a hostname cert, you can either combine them all in a single cert and have that be short-lived, or you can have one cert on one renewal cycle for the IP and one cert on one renewal cycle for the hostname or multiple host names.
Yeah, I mean, for my particular case, it doesn't make much sense because you can always create a subdomain and that is faster. But is this more focused on enterprise kind of things?
Yeah, I mean, part of the reason it's taken us so long to launch them is like there's not a super compelling use case in terms of like traffic on the internet. Kind of consumer level traffic. There's a lot of people who want it for like intranets or whatever, or like, oh, you just spun up a cloud instance and you want to securely communicate with it. Our like guiding star is that we want people's communications to be private on the internet. So like most people, most of the time they're browsing the internet, they're going to a domain name, not an IP address. However, actually, like IP addresses are used in a lot of cases for censorship resistance. If somebody like keeps taking down your domain name, or like you can't get access to the domain name system for whatever reason, you don't have a payment method, or no registrar wants to talk to you, often you can use an IP address instead, and we want that traffic to be secure. And there's a lot of other like various use cases. So.
But you cannot sign, you cannot get a certificate for, I don't know, 164, or what kind of, like the private.
Exactly, yeah. So 10 dot anything,
Yeah,
192.168, 127.0.0.1, which is really a bummer. Like it would actually be like really nice for every machine to have a locally trusted cert that was valid for a local host. And when you're developing like a website on your machine, it just acts like an HTTPS website, because if you've done any web dev, it just acts really different if it's not HTTPS. And there's good reasons for that. You don't want to be able to turn on the webcam from an HTTP site, because you could be getting man-in-the-middled. But this is like kind of a repeating problem where people try to issue a certificate for a host name that happens to resolve to 127.0.0.1, and then they publish the private key for that. To help everybody out. And honestly, like I love helping people out, and I wish they were allowed and we were allowed to help people out that way, but as a CA we are required to revoke those certificates when we find out about them, and we have to do it manually, which makes it a hassle. So please avoid doing that. There actually are some pretty great tools. I can recommend MKCert for doing this kind of locally trusted issuance, because the ideal is like, I don't want my local host to be the same as your local host, and I don't want it to have the same pub key, and if somehow you get me to talk to your local host, I don't want my browser to think that that's my local host. And so that's why like a different root for everybody's local host is great. MKCert does this. It installs a local root. It issues from that for your local host. It's pretty cool. And of course, we are both nonprofits. We thank you to all the members here. I hope some of you are inspired to become members from my visit today. EFF and Let's Encrypt both operate on donations. EFF also, in particular, loves having more members. We have 40,000 members, and when we go to Congress and say, hey, like you need to do this, by the way, we have 40,000 members, like that really means a lot. So even if you can't afford to give a lot, becoming a member is great, and if you can give a lot, also great. So yeah, any questions?
What is the revenue for like Let's Encrypt? I mean, it's amazing that I've been able to get free certificates
Yeah.
for like years now, but like what's the main
So yeah, it's
revenue?
literally donations, grants, and sponsorships. So we get some fairly large sponsorships from big companies. You can see on our About page, various entities that use us or just like want the internet to be more secure give us money. We also have gotten a few grants here and there. Grants are, can be tricky because there's not a lot of organizations that want to make a grant to just like keep doing that great thing you're doing. They usually want you to have a project. We do like to have projects and we like to launch features, but we also like to keep the lights on and make sure the site is really reliable and fast and all that stuff.
My question is about the scale of Let's Encrypt. I
Yeah.
mean, what kind of infrastructure is it running on? What does that cost to operate, that kind of thing?
Yeah, I would want to refer you to our annual report on that because I don't want to say too much about our infrastructure, and also like I think some of the numbers are there in terms of costs and so on.
Okay.
You go ahead.
I've just heard some scuttlebutt about certificate authorities who issue application certificates, application signing certificates.
Yeah.
As kind of colluding perhaps and raising prices and shortening lifespans. And I was just wondering if Let's Encrypt was thinking about application signing certificates at all?
It's interesting. It's not an area we've explored. When we launched, we were like, yeah, we might get into kind of other areas of certificates. But one of our other guiding stars is automation. We are able to scale so much and do this for free because we can automate so much. And application signing certificates are more kind of like, depending on the ecosystem, a bit of they can be interpreted as a stamp of security or approval or whatever. When we sign a certificate for a website, we are saying, yes, we would like you to communicate securely with this website. We have no idea what's on it or whether they're any good or whether they're fraudsters or not. And with application certificates, that's a lot harder. There's also a lot more kind of, hey, I lost my key, can you reset it for me? Or that type of escrow scenario for the application developers. So it's less of an appealing market. But yeah, it is a lot of money to get your application signed these days. That's not great.
Do you think the shortening of the lifespan of certificates might have to do with getting quantum resistant certificates?
I think probably not. I'm not as familiar with the application software side of things. I do know, and this is something that would be useful for you all to know, on the web certificate side of things, lifetimes are coming down. So when Let's Encrypt launched, I think the longest certificate you could get was 5 years. And we decided we're actually going to do 90 days, which was explosively controversial at the time. Longest forum thread in the history of Let's Encrypt, locked after several hundred replies. Because we're like, well, these are going to be automated. So it shouldn't be a hassle to renew it every 60 days. It should be automated. And a lot of people said, well, I have these things that I can't automate. And that is true, but our belief was that over time, more and more stuff would be automated, and that's been the case, and it's been a big benefit. And browsers also have agreed, and slowly the times have ratcheted down to 2 years, 1 year. Pretty soon it's going to be, I think, for everybody, max 90 days, and then it'll be max 45 days. And so we actually have some changes coming up, too. Our max length is going to go down from 90 days to 45-ish days, in addition to the really short 6-day certs that we offer. And the reason for shorter certs is that if a cert is bad for whatever reason, it was issued in error, or mainly if it was issued in error, like say to the wrong entity, like a man in the middle, you can revoke it if you find out, or it can just get gone after 6 days. And that's just a little more reliable than the revocation mechanisms, even today with the Bloom filter stuff I mentioned. Yeah.
How does the scale work out for all of these short-lived certificates? Because if they're so much short-lived, you're going to issue so many more of them. How does that become manageable with that level of activity?
It's hard. This is one of the reasons all this stuff is so exciting. So CT logs are actually one of the big areas where it's really hard, because it's like, oh, you have to store all this stuff in a specific way and sequence it. And so making CT logs capable of handling much larger volumes is kind of a precondition to shorter-lived certs. But also our own infrastructure of just we do validation and we record it and we keep the certificates around so we can revoke them and so on. That is going to have to increase also to match shorter-lived certificates. So we are building out our infrastructure. We're adding more bigger machines. We're also re-architecting. If you follow the Boulder repo, you can see we're moving towards Vitesse so that we can horizontally shard stuff. Yeah.
So maybe I misunderstood, but you're storing every single certificate ever created, or you purge the ones that are already tooled?
So in a CT log, actually the original concept of a CT log was every cert ever created, because when it was first developed, there were maybe 5 million certs in the wild. And now there are billions. And so now CT logs are sharded. You have one a year, one every half year. And then we used to keep old logs around in read-only mode for a while, but even that gets kind of expensive. So now it's actually Filippo Valsorda, who pushed a lot of static CT API stuff and a lot of other cool things, developed an archiver to push old logs into the Internet Archive and say, here's a just giant file. You please hang on to it. We're going to shut down this live log because it's expensive.
Are there any unique security or identity verification challenges with issuing IP certs versus domain certs?
Yeah. So Let's Encrypt has 3 main challenges we implement right now. Oh, and actually I should tell you about the 4th that's coming soon that's pretty exciting, called DNS Persisto 1. But so the ones we have now are DNS, HTTP, and TLS Alpin. So for the HTTP challenge is like, put this file on your web server. We fetch it, nice and easy. And that works great with IP addresses. You just connect to the web server and you say in your host header either that IP address or you leave it blank and the web server hopefully understands what IP address it was listening on and it returns the right file. Beautiful, easy. TLS Alpin is we connect over HTTPS and the web server serves us a special cert that is like, has it kind of like the file, but it's at the TLS layer instead. And we happen to stick the magic number in the subject alternative name field, which is like where the host name normally goes in a cert. And the specs say, oh, you're not supposed to put an IP address in there. It's just not allowed to be right there. So we rewrite the IP address to be in the inattr.arpa zone, which if you've ever messed around in is ridiculous. And particularly for IPv6 addresses, is you got to dot every little octet.
0, 0, 0, 0.
Yeah. So that's just messy, but it works. And then actually DNS-01 just doesn't work for IP address certs, which is a bummer. We talked about, oh, well, you map that to the inattr.arpa zone and you look it up, but actually the management of the inattr.arpa zone is really inconsistent, and there's just no guarantee at all that the person who controls the inattr.arpa for your IP address is related to you at all. And so there's pretty serious risk there that some unrelated entity could get certs for your IP addresses. So we noped out of that. And I feel like there was one other aspect kind of related to the inattr.arpa, but it'll come to me. The other thing that's useful to know is, so the DNS challenge, it's like, here's a token, you put it in your DNS at _acme-challenge.example.com. We fetch it. This is actually my favorite challenge. If you ever wondered if I had a favorite Acme challenge, I love DNS-01 because every other challenge depends on DNS. And so you might as well just do a DNS. It gets you actually like a higher level of assurance. We do less work. A DNS request is much cheaper than, it's all cheap, but it's like cheaper, simpler than HTTP. And also, one of the vulnerabilities of like how CAs do validation today is stuff goes in the clear. And so like if somebody can do, say, a BGP hijack for that initial query, they can just serve us bogus garbage. And so like somebody could get us to misissue by hijacking the route for like the authoritative DNS for somebody, or for hijacking the route for their host name. For challenges that don't rely on HTTP, doing a BGP hijack for their host name doesn't help. Still hijacking their DNS server helps. But then you can apply DNSSEC. I have a lot of gripes with DNSSEC. It's a hard protocol to deploy. It's more likely to take down your site than protect you from an attack. But I will say, actually, like one place where it really does its job is in the initial request from your CA to validate you. We as a CA do validate DNSSEC. That is now mandatory. So if you want kind of cryptographic verification from your domain to your CA, you can deploy DNSSEC for your domain, and that DNS request will be protected. There's one other thing you have to do, which is install a CAA record. Very briefly, CAA is a special kind of DNS record. You can put into place to say, I only want this CA to issue for me. And you can also say other stuff like, I only want the CA to issue for me, and I only want this CA to issue for this account. So if you really want to like lock down certificate validation, you would do DNS-01 validation. You would put in a CA record saying, only Let's Encrypt, only this Let's Encrypt account. And then you're like pretty solid. But it's also a big lift, and DNSSEC is more likely to take down your site than keep it safe. But it's a great learning experience. This was all in service of DNS persist 01. So the thing that's annoying about the DNS validation method is, like all Acme methods, you have to revalidate every however often you want to renew, which might be 60 days with current certs, more often otherwise. And that's fine. You can automate it. You can have a plugin that knows how to talk to your DNS provider and put that token in. And you can have the credentials for your DNS provider just sitting on your web server. But maybe you don't want that. That's actually like a big risk profile. Like that is a higher level of privilege than your web server ordinarily can do. If somebody gets into your web server, normally they can't change your DNS. But if you happen to have credentials sitting around so you can do the DNS-01 challenge, now they can change DNS for your whole domain. It's a big mess. but you kind of need that, or you need something more clever. If you want to get clever with what's available today, you can have your Acme client off somewhere else doing validation and then pushing the certs to your web server. Kubernetes, yeah, there we go. But so DNS Persist 01 just became legal by ballot at the CAB forum, and the idea here, well, arguably just became legal versus was always legal. Really what people would like to do is put a token in their DNS once that says, this is the CA I'm using, this is a random token that CA generated, this is like maybe my account, you actually need that binding, and then just leave it there forever. The CA does periodically need to revalidate that in terms of fetching the token, all this junk, but the user doesn't need to change it all the time. It's like one thing that attests to control for all time, and so this will let people do that, say, manually through their DNS provider once, and then renewal can still happen automatically without putting your credentials on your host. So there's a IETF draft in progress. We're planning to implement and deploy it eventually. And I think that will really be the cool stuff. Yeah.
Yeah, maybe I missed it. So how is like CT logs going to be? It seems like it's fairly newish or something. So how is it going to be like used?
Yeah.
This is like I must have missed that idea. How are you going to implement that with other CAs? Are you going to collaborate and like share those logs and like try to prevent some of that riffraff that's happening on the internet today?
So certificate transparency is live. It's required in all certs today. It's been going on for 10 plus years, and it's working. So there's a bunch of CT logs, but they keep falling over or just being like, operators are like, I can't do this anymore. So that's what static CT is about, is making it orders of magnitude cheaper to run a CT log. So more entities can do it, and the existing entities can keep doing it into the future as issuance continues to increase. And then the Merkle Tree certificates concept is what it needs kind of coordinated deployment and so on. And so several of us are in that IETF group. We're kind of following developments. At some point, we will probably produce or deploy a implementation for interop testing. And then at some point, over time, we might make available, oh, hey, here is our realistic prod-like implementation of it, try to issue certs against it. And then one of the real blockers is going to be, when do browsers accept it? But to get to the point where browsers are willing and ready to accept it, there needs to be an ecosystem demonstrating willingness to deploy it also. And there's also an important missing piece of, well, Merkle Tree certificates are something specifically we want to deploy for post-quantum cryptography. And so all these signatures are going to need to be post-quantum, so MLDSA. The status quo today is we're doing ECDSA signatures, we're doing RSA signatures. The private keys for those are in an HSM. How many people know what an HSM is? Cool. Hardware security module. So and actually hardware security modules are basically glorified Linux boxes with all the seams glued shut and with special software, but they are the core. The primitive they export is you can create keys on them that you cannot export, even if you have root access. And they have a lot of tamper-proof mechanisms and all sorts of stuff. But when we create an intermediate CA cert, we create it on an HSM, so the key is in there, and we can sign objects with it, but we can't just take it out and copy it and publish it on the internet. And that's a requirement. All CAs have to use HSMs for their signing keys, because that's just kind of basic good practice to keep things secure. And so to do MLDSA, whether it's in the straightforward, boring way that generates giant certs, or in the Merkle Tree cert way, will require HSMs to be available that can generate this type of key and can sign with it, which isn't the case today, but I think will become the case.
Cool. So are the other CAs so far been pretty receptive to this kind of collaboration? And you don't have any problems in the space with that kind of thing?
Yeah, I think the other CAs that are excited about post-quantum certificates are also excited about these concepts, because well, how are we going to actually get this deployed? This is something that, I think CAs actually get a lot of questions from their savvier customers to be when are you going to do post-quantum? How soon can we get there? Because, like I said, the deployment time is now.
Yeah, sure.
Yeah.
I got a question.
Yeah.
So you hinted at this earlier, but currently, I mean, we have so many CAs that we do have to support in a browser.
Yeah.
And as long as we have like, even one bad CA out there and get a bad certificate for a website, how far are we to being able to just drop arbitrary CAs from the standard browsers and be able to trust something that's a little more automated, a little more authenticated or whatever?
Yeah.
This long list of CAs that you can't drop easily.
So do you mean like as an end user, like could you take out some of these CAs and distrust them personally?
I mean, when I've looked at the list before, just so many entries in there, and I don't know how many of those I can safely delete. And
Yeah.
yeah, I mean, like Let's Encrypt. At least I know how they validate and stuff, and certain entities I can trust. But there's so many in there. The browser trusts them all equally, to my understanding.
Yeah.
So.
Well, and I will say there is some slight complexity to that. There are some, so browsers have some complex validation logic that will sometimes say, oh, well, this root CA is in there, but we're not going to trust them for any certs after date X, or we've applied various other limitations to them. But that still leaves a lot of generally trusted CAs. I think the problem is if you remove an arbitrary one of those, you might not see anything happen for a while. It might all be fine, and then one day you try to load a site and it's like, yeah, cert not trusted, and you've forgotten that you removed the cert, and that one site happens to use the CA that you took out. And there isn't really currently a way as an end user to be like, I wish that site would use a CA that I trust. They use the CA they use. There was a project back in the Firesheep days, 2010, to do kind of perspectives validation to say, well, okay, yeah, that site is using some CA that you don't trust, or maybe they're even using a self-signed cert. But these multiple perspectives on the internet have all attested that this is the cert that's live there, so that's probably good enough, and you should trust that. But it doesn't really exist today. It wasn't a great approach for complicated reasons. I think the short answer is you can go ahead and distrust CAs locally, but you might break some stuff on the web. And you might not notice it because it might actually be a sub-resource, some JavaScript from a CDN that fails, and you would just be like, well, this page is all gobbledygook, and it's because of some sub-resource that you have to find in the dev console. But feel free to experiment.
Yep. And I also remember when I had worked with the government for a while, for a few years, they specifically did not trust any of the public entities out there. They ran their own CA.
Yeah.
One that was not in through browsers.
Yep.
And so the first thing to do before accessing any of their websites was to go and download the DoD root certificate 1 and 2, and install those in your browser so that you can start accessing the government websites. After the download arbitrary certificates just to even access the site, that's worse than trusting some third-party CA that at least is in my browser.
Right.
Already.
Yeah, I mean, this is the tricky thing is actually for intranets, often it's actually best practice to have your own internal CA for reasons well, public CAs are bound to the policies of the browsers, which can change. And so, for instance, sometimes CAs have been required to do mass revocations of certificates they issued in error. And enterprises often want more stability of being we're going to make that choice. This is our CA. And so there's big advantages to hosting your own PKI. But the big disadvantage is, well, yeah, the only devices that can kind of automatically access stuff on the intranet are the ones that we manage and we've installed that root on. And inevitably, people are going to want to be accessing that from some unmanaged device, and then you have them installing arbitrary roots, and it's a mess.
I wonder if this is a good time to pass around.
Oh, yeah, let's take one and pass it down, I guess, left and then zigzag, and we'll come back up here. So yeah, some nice Let's Encrypt stickers. I couldn't find my EFF stickers today, unfortunately, but these are, I think, rarer.
Walking around with a stack of, but let's do the government sticker would be pretty cool.
Oh, that would be great. Yeah. Well, if you become a member, we'll send you hella stickers. So good reason to become a member.
So you talked about, I forget how you said it, incompetence is identical to malfeasance.
Right, exactly.
Which makes sense, but also these things are terabytes.
Oh, yeah.
And there's not that many of them. And what's the process for saying, okay, you screwed up, but you can learn your lesson and come back to the party? How do you manage that in a way that both preserves trust and also recognizes the fact that these are hard?
Yeah, I mean, so much of it happens in public, and this is kind of modeled on what's been going on the mozilla.dev.security.policy mailing list, and prior to that, Usenet group for years, which a lot of CA-related stuff just gets discussed in public there, and anybody can post and say, hey, I saw the CA doing this thing weird. The CA can post there, and there's also actually a process for filing incidents in Bugzilla and collecting public feedback. And so similarly, in parallel for certificate transparency, there's a CT policy mailing list. And all the log operators are on there. And people can report, oh, hey, I saw this log do this incorrect thing. And log operators are kind of expected to follow along and be like, oh, hey, oops, thanks for pointing that out. Or, oh, yeah, we know about that, and here's what's happened. And we have had bit flips that have been publicly discussed on the mailing list. And people can kind of hash out the details, and in that case, it was actually yeah, because of this bit flip, we that has then been, the results have been signed. We can never recover the cryptographic validity of this log, so that particular log is going to get distrusted. But because you could so obviously determine the symptoms, oh yeah, this was a bit flip. It wasn't something was swapped in there. The log operator isn't looked on as they did something bad. It's oh, this is an understandable mistake that is just a consequence of existing on the planet Earth. And
so you just wait until the 6-month rollover essentially, and then you're okay again?
Yeah. So basically
as
that.
long as they have a decent explanation.
Yeah, exactly. And in general, they will already, so at any given time, log operators will usually have several shards in operation because you have to pre-qualify them. So this is one of the things browsers do is you say, oh, I have this new log shard I want to do. And they're like, great, we want to submit stuff to it over a certain period of time and test that it works and stuff gets incorporated. And then you get qualified. And then from there, so the browsers push this data to all their the individual machines that run the browser, but that can take a long time. And so the way this works is the code in the browsers say, if I haven't updated my list for more than 6 months, I'm going to start ignoring CT. So you get a little less safe if you haven't been getting those updates, but at least the web continues to work. And so within 6 weeks after the update has been pushed to the log list, you know that everybody either trusts your log or doesn't care about logs anymore. And so at that point, that log is safe to use in newly issued certs. So I think in that actual case, it was okay, the log that had the bit flip is going to get rejected, but the other shards that you have pre-qualified are going to be fine, and those are the ones that are off into the future. Yeah. And actually, I mentioned the bit flip, which was another log operator. We at Let's Encrypt had a weirder kind of database error that also resulted in bad results. And that one actually didn't affect the cryptographic identity. But somebody pointed out, and we were like, oh yeah, we can see how that got screwed up. And we were able to dig through our logs, put everything back in the right place, and restore the correct operation of the log. And that was also fine. Anything else? These have all been some great questions. Thank you very much for being so curious.
Thanks for talking. Thank you.